Students, today we are going to study power in AC circuit, alternating current circuit. The rate at which electric energy is consumed in an electric circuit is called its power. In a DC circuit, power is given by a product of voltage and current. But in an AC circuit, both voltage and current vary sinusoidally with time and are generally not in phase. So, for an AC circuit, instantaneous power is defined as the product of instantaneous voltage and instantaneous current. Let E be the instantaneous voltage, which is equal to E naught sine omega t, and I be the instantaneous current, which is equal to I naught sine omega t minus phi, where phi be the phase angle. Okay, phi be the phase angle by which voltage leads the current. So, we can write instantaneous power P is equal to product of instantaneous voltage and instantaneous current, that is EI. Substituting the values from these two equations, we can write P is equal to E naught I naught sine omega t into sine omega t minus phi, or we can write P is equal to E naught I naught upon 2 into 2 sine omega t into sine omega t minus phi, or we can write for this bracketed term, we can write cos phi minus cos of 2 omega t minus phi as 2 sin A sin B is equal to cos A minus B minus cos A plus B. Therefore, we are having P is equal to E naught I naught upon 2 into cos phi minus cos of 2 omega t minus phi. Average power dissipated per cycle is equal to average of instantaneous power. So, here you see the second cosine term, cos 2 omega t minus phi. The second cosine term is time dependent. Its average over a cycle will be 0. So, P average we can write, here you see average power dissipated per cycle is equal to average of instantaneous power or average of power. Okay, P average is equal to E naught I naught upon 2 cos phi, because second cosine term is time dependent, so its average over a cycle is 0. Here for this quantity E naught I naught upon 2, we can write E naught upon root 2 into I naught upon root 2. Root 2 into root 2 will be 2 only. That's why P average is equal to E naught upon root 2 I naught upon root 2 cos phi. For this quantity E naught upon root 2, we can write E RMS, and I naught upon root 2 we can write I RMS cos phi, or we can write P average is equal to E RMS I RMS R upon Z. For cos phi we can write R upon Z. Students, now we consider some special cases. First case is pure resistive circuit. Here the voltage and current are in the same phase, that is phi is equal to 0 and cos phi is equal to 1. Cos 0 degree is 1. Substituting the value of cos phi here, we get P average is equal to E RMS I RMS into 1, that is P average is equal to E RMS into I RMS. Using Ohm's law, that is V is equal to IR, we can write P average is equal to E square E RMS square upon R. Second case, pure inductive circuit. Here the voltage leads the current in phase by pi by 2. Cos, if we substitute phi is equal to pi by 2, cos pi by 2 will be 0. Substituting the value of cos pi by 2, we get P average is equal to 0. Thus, the average power consumed in an inductive circuit over a complete cycle is 0. Number 3, pure capacitive circuit. Here the voltage lags behind the current in phase by pi by 2. That is, we can write for phi minus of pi by 2. Therefore, P average will be E RMS into I RMS into cos of minus pi by 2. Substituting the value of cos pi by 2, we get P average is equal to 0. Thus, the average power consumed in a capacitive circuit over a complete cycle is also 0. Fourth case is series LCR circuit. For a series LCR circuit, P average is equal to E RMS into I RMS cos phi, where phi is equal to tan inverse xi L minus xi C upon R. Sometimes phi may have a non-zero value for series LC, LR and LCR circuit. So, power is consumed in such circuits but only in resistor R. Fifth special case is power dissipated in resonance in LCR circuit. At resonance, we have some special condition, that is xi L is equal to xi C and phi is equal to 0. If we consider cos phi, that is cos 0 degree, cos 0 is 1. So, P average is equal to E RMS into I RMS value. That is, maximum power is dissipated in the circuit through resistor at resonance. Power factor. Since P average is equal to E RMS into I RMS into cos phi. The product of E RMS and I RMS. Product of E RMS and I RMS does not give the actual power and is called apparent power. It gives actual or true power only when multiplied by a factor cos phi. The factor in this relation, the factor cos phi, is called the power factor. Once again, I am repeating. In this relation, E RMS, I RMS, cos phi, the product of E RMS and I RMS does not give the actual power and is called apparent power. It gives actual or true power only when a factor cos phi is multiplied by this product. The factor cos phi is called the power factor of an AC circuit. So we can write true power is equal to apparent power into power factor. From this power is equal to apparent power into power factor, we can define power factor. See, power factor is defined as a ratio of true power to the apparent power. Mathematically, we can write power factor is equal to true power upon apparent power. Since power factor is cos phi, so its value varies from 0 to 1, as cos 0 degree is 1, cos 90 is 0. The power factor of a series LCR circuit is cos phi is equal to R upon Z. You remember once we have drawn impedance triangle, and from that impedance triangle we can write cos phi is equal to R upon Z, where Z is impedance. Substituting the value of Z, we can write R upon square root of R square plus omega L minus 1 upon omega C whole square. For a purely inductive or capacitive circuit, phi is equal to 90 degree. So, cos 90 degree, that is power factor. Power factor is equal to cos 90 degree, which is equal to 0. For a purely inductive or capacitive circuit, power factor is 0. Thus, the power factor assumes the minimum value for a pure inductive and purely capacitive circuit. For purely resistive circuit, phi is equal to 0 degree. So, cos 0 degree is equal to 1. In this case, for a purely resistive circuit, the power factor assumes the maximum value for a purely resistive circuit.